Okay, so when we look at these problems, when we look at each of the different elements, we want to make sure that we can recognize that Na is a symbol for a single element, sodium. S is a single element symbol for sulfur, and O would be oxygen. So that gives us 3 different elements in this compound. Now, in terms of sodium, we want to make sure that, first of all, we pick out sodium as Na. And then we also want to recognize that in this particular compound, we do have a coefficient of 3 in front. So remember, that is telling us that we have 3 molecules of this compound of NaSO43. So if we're just looking at one molecule, we would have 1 sodium atom. But because we're looking at 3 molecules, we have a total of 3 atoms of sodium. Next question, how many atoms of sulfur are shown? So here's our sulfur, and we want to remember that the 3 subscript outside applies to the oxygen. It also applies to the sulfur. So that 3 outside is saying that we have 3 SO4s, just like we've got right here that I just wrote. And so 1 sodium is attached to 3 of those guys. So if we want to figure out how many atoms of sulfur are in this compound, then we're going to have to do 3 times 1, which is a total of 3 when we have 1 molecule of it. But since we have 3 molecules of it, we're going to multiply that times 3. So that's going to give us a total of 9 there. And then finally, how many molecules do we have? We have 3 molecules. That's what the coefficient of 3 gives us there. Please check number 5, 6, and 7 to see if you did your balancing correctly. I'm going to go ahead and I'm going to erase my answers for number 7 and kind of show you how I work through that one, because that one's the hardest one on this page. So if we first do our starting atom counts for each of our different elements, we've got carbon, hydrogen, and oxygen. So we have 2 carbons, 2 hydrogens, and 2 oxygens. And then coming out, we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens. So one of the first things that I can recognize is that going in, I have to have an even number. And the fact that water over here doesn't have an even number, that's going to cause a problem for me. So I'm going to go ahead and I'm going to put a 2 in front of the H2O so that way now I'm going to have an even number of oxygens, because I have 2 of them in the carbon dioxide and then I have 2 of them in the 2 molecules of water. So what that gets me is 4 oxygens coming out. But that also has now impacted my hydrogens to 4. So now that I've done that, I'm going to go ahead and I'm going to try to fix this issue. So if I put a 2 in front of C2H2, that's going to give me my 4 carbons that I want. It's also going to, it's going to give me my 4 hydrogens that I want, but it's going to mess up my carbons. So that was good and that was bad, but I can go ahead over here to my carbon dioxide and I can put a 4 in front there. And that's going to give me my 4 carbons. But that's also going to change my oxygen. So I'm going to do 4 times 2 means that I have 8 oxygens, plus 2 times 1, I have 2 more of them. So I have a total of 10 oxygens. So this is actually pretty good. My carbons are equal across, my hydrogens are equal across, and I know 10 is an even number. It can be divided by 2. So right here, I can put a coefficient of 5, and that's going to give me 10 oxygens, and I'm balanced there. If you scroll on down or go on to the next ones, I want you to notice a couple of things that I do when I'm working on these. I do put the charges above so that when I make the formula, I make sure that the charges are balanced. If your charges are not balanced out to 0, for example, with the silver carbonate here, if you wrote that as AgCO3, you're not going to be able to get things balanced correctly. Or if you wrote iron 2 chloride as FeCl, again, you're going to have a hard time with balancing. So you want to first make sure that you're writing your formulas correctly. Make sure that you're labeling those different charges so that way, for example, with the silver carbonate right here, I'm going to need 2 silvers so that way I get a total of positive 2, and that's going to balance out to 0 with the negative 2 on the carbonate. So if I don't do that originally, I'm going to have difficulties. So again, this goes back to last semester where we're checking those charges. Please remember that the 2 after any transition metal, that tells us the charge. And again, you can make notes on your paper right now as I'm going through this to help you with studying. This would be a double replacement reaction. We have a compound and a compound, and we can see that the iron and the silver have switched places. So this is going to be a double replacement reaction. For number 9, we have gold 3 oxide. Again, recognize that I put the charges right there above, and it's breaking down into its elements. You want to always make sure to watch for those diatomic molecules. Remember these 7 as being ones that are not going to be okay when they're alone. So if they are not in a compound, again, not in a compound, they're automatically going to be a 2, so H2, O2, Cl2. This reaction here is decomposition. We're starting with one material, and we're breaking down into 2 separate materials. And then, of course, we need to make sure that we balance, so check your coefficients in front. And then the next one, again, one of the places that I start with balancing is I look at this polyatomic ion right here. I see that there is a 3 outside of the parentheses, so I start with putting my 3 right there because I don't have carbon or oxygen in any other place. So once I get started with that kind of approach, then I can work on getting the rest of them balanced as I work from there. When we write the formulas, again, we want to look at the chlorine's charge to figure out what the charge on the iron is. So chlorine gets a -1 charge, but we have 3 of them in this compound's formula. So that means we have a total of a -3 charge. So that means to balance to 0 with that -3 charge, that iron needs a +3 charge. So that's how we come up with this as iron 3 chloride. Then we can say and for the plus sign. Sodium is Na. And then we just name our polyatomic ion for carbonate. And then right here for reactiform, we could also say makes, we could say yields, we could say produces, anything that's going to transition us to our products. And then we get our products. So Na is sodium, Cl is chlorine, so we change that to chloride. Iron still has the same charge on it, so it's still iron 3. Once you've got the charge of iron figured out, it's not going to change. And then we have carbonate, and this is a double replacement reaction. And then we've got the last problem, which is probably the trickiest on this practice exam. So I'm going to go ahead and I'm going to erase my counts here, and I'm going to kind of show you how I worked through this particular problem. So what I did is when I first did my original counts, I looked at the fact that I only had 1 aluminum coming out, but I have 2 aluminums going in. Sulfur, I have 1 sulfur going in, but I have 3 sulfurs going out. Now, oxygen and hydrogen are tough ones because they're in 2 different places. So I'm not even going to do my starting counts yet. I'm just going to look at aluminum and sulfur, and I'm going to put in some coefficients to get those balanced. So if I put a 2 in front of the aluminum hydroxide, that's going to get me 2 aluminums, just like I want. If I put a 3 in front of H2SO4, that's going to get me 3 sulfurs. Now I'm going to deal with the oxygen and hydrogen because those are the tough ones to deal with. So now that I put those coefficients in, I've got to be careful. I have 3 times 1 hydrogen times 2 is 6. So right here I've got 6 hydrogens, but I have another 6 hydrogens here. So that means I have a total of 12 hydrogens. I'm going to look at also my oxygens. So if I look at my oxygens, I have 3 times 1 times 2. So that means I've got 6 oxygens here, and then I've got to be careful. 4 times 3 means I've got 12 oxygens there. So this means I have, I have 18 oxygens, okay, coming out. Now, I'm going to look at my hydrogens and oxygens over here. I have 3 times 4 of them, so I have 12 oxygens, but then I have another one here, so I have 13 oxygens. Now, if I look at my hydrogens, I have just these 2 hydrogens right there, okay? So, start with the hydrogen, because you've got a nice even number of them. So I've got 12 hydrogens. I can easily get 12 hydrogens over here. 6 times 2 is 12. So I got that. Now I'm going to check my oxygen counts. So I didn't do anything over here. I still have 12 oxygens over here. And 6 times the 1 oxygen means I have 6 oxygens. So I got to add those together, which means that I have 18 oxygens, which is exactly what I need. Okay? Again, double check that you wrote it in words correctly. This is a double replacement reaction.